Everybody, and welcome back. So for today's video, we're going to be taking a look at our next step in the progression of our area problems. And today we're going to be focusing on something called definite integrals. So just that name should sound familiar. So in this unit already, we have taken a look at another version of integrals called indefinite integrals. So indefinite integrals was the idea of anti-differentiation, when I would start with one function and then use the anti-differentiation process to go backwards. So just for the sense of ease, think of starting with a derivative function f prime. Using anti-differentiation, we can go back to the graph or the function of f of x. We can do that in a general sense where we have the plus c's, or we could use find particular solutions given an initial condition where instead of just a placeholder plus c, we actually find the real constant value. So that was the indefinite integrals process and how we find them. But today we're going to be taking a look at definite integrals. So this is kind of the beginning of a transition process or a connection piece between our area stuff and the integral notation and the anti-differentiation process. This is kind of laying the groundwork, but next section we're going to really see how those two things are actually directly connected to one another. But first, we have to get used to a different kind of notation to represent our area problems. So that's kind of the focus for today's topic. So if you recall from last section, we discovered a method for finding the actual area under a curve by applying a limit to that sigma notation. The sigma notation represents a generalized method of approximating the area using n equal subintervals. And again, when we use sigma, we're always using rectangles as that defined shape. Again, the purpose of that was to have a repeatable process that's very efficient. So then because it's repeatable, we can use the sigma notation to represent those repeated iterations. And then when I take the limit of that notation, that gives us our actual area. So again, the idea of that limit was when I take n, the number of subintervals, and I increase it to infinity, that kind of fills in all the space, and it's no longer an approximation, but we're really finding the actual area. However, though, there's one piece to that puzzle, and it has to do with the width of our subintervals. So most of what we did already focuses on equal subintervals because that's the easiest way to do it and the most easily repeatable way to set it up. But we have seen some examples already where we used unequal subintervals to approximate that area under the curve, but all of those used a fixed number of subintervals. So if you remember back to the second section where we were still doing the approximation models, not finding actual area, but there were some problems. Typically, we see these when I give you a table of values and we don't have an equally spaced values of x. But we can do it really in any situation, whether it's a function or a graph, but it is possible for us to approximate with unequal subintervals. Well, we can actually use any width of intervals, doesn't matter whether they're equal or unequal, to find the actual area under a curve. So because it's possible to create an approximation using unequal subintervals, we're going to kind of generalize that process and just say that this symbol, delta x sub I, is going to represent the width of each different subinterval. So no matter what size they are, doesn't matter if they're equal or unequal, this guy, delta x sub I, is going to represent the width of each different subinterval. So again, that works kind of the same way. C sub I represents the particular endpoint that I'm choosing to use, typically right endpoint. But when I is 1, that would be C sub 1. So that's the first subinterval's right endpoint. When I equals 2, that would be the second subinterval's right endpoint, and so on. Delta x sub I now just represents the varying widths for each one. So for the first subinterval, when I is 1, that's its width. And then when I equals 2, now we have a new width. It might be the same thing, might be something different. So it's just a commonality or a generalization, a different way to represent that same concept of width for these subintervals. Now, however, if the subintervals are in fact different sizes, then we kind of have to approach this just in a slightly different way. So I want you to imagine the largest subinterval possible in any particular region, okay? If I take that largest thing and we force that to approach 0, if the biggest one gets shrunk down to 0, then all the ones that automatically have to be smaller than that also have to get shrunk down to 0. So in a roundabout way, so just so that we can cover all of our bases and account for any possible scenario, whether it's equal intervals or unequal, by taking the maximum possible value for delta x sub I and forcing it to go to 0, that forces all of the widths to go to 0. And if all of the widths go to 0, then that in turn will force our n value to head towards infinity. So the only way that I can cover the region with rectangles whose widths are approaching 0 is if I have an infinite number of those rectangles to account for all that space. So what that does for us is it really doesn't change anything about our process, but now we've accounted for every possible scenario when we are using these rectangles to estimate the area of these regions. So unequal widths with the repeatable process is really the only thing that we haven't looked at yet. So notationally, what that means or how that looks is we're going to start with a slightly different limit notation out in front. So instead of starting with as n goes to infinity, we're actually going to start with the maximum delta x sub I value will approach 0, but that guy in turn will turn into the limit as n goes to infinity. So here you see that delta x sub I, that's also different. Again, we're accounting for possibilities where it's different. But as soon as we take this maximum and we force it to 0, we can kind of revert back to our original notation. But this is just kind of like us at the beginning saying, okay, I'm going to account for every possible scenario. But as far as our math goes, it's really going to operate the same way. Okay? So that's just one kind of new thing that we have to account for that we haven't specifically looked at before. So now that that's out of the way, now we're going to be translating stuff into our new notation. So again, history lesson, different mathematicians, Newton and Leibniz, had their own notation and systems for both kinds of calculus. Differential calculus with the derivatives, we've already seen that difference in notation. We're talking about the difference between f prime and dy dx. But now when they looked at integral calculus, or the idea of finding the area under these curves, they also each had their own systems of notation. So we kind of have to be able to bounce back and forth, but again, one of these is a much simpler way of representing the information, and that is the idea of a definite integral. So the idea of a definite integral, this is the notation that Leibniz promoted, and it's really been adopted throughout the world of calculus. Not too many people prefer to work with these sigma notations. It's just very clunky, and it's not a fast, easy way to represent our problems. So what we're going to focus on right now is being able to translate the way we've been doing things with our sigma notations and limits, and translating it into Leibniz's notation with these definite integrals. So one thing to keep in mind is the difference between the kinds of integrals, and we're going to talk about that here in a minute. So, but the main idea is our sigma notation represents the area under a curve from one value of x to another. That's our a and our b. Well, the one issue that most mathematicians have with the sigma notation is nowhere in here does it state what that a and b value are. We can kind of work backwards and pick out the information because we do have some of that kind of hiding. Our delta x formula is created using a minus or b minus a, so we can figure out the distance between the two. And our c sub I notation, remember, that revolves around a. So it's either a plus delta x times I minus 1 if I use the left endpoints, or a plus delta x times I if I use the right endpoints. So with those two pieces of information, we can work backwards to figure out a and b, but we have to do a lot of legwork to find that. So that's the one major drawback to using this notation. However, when we translate this into a definite integral, it's a much easier way to represent really all the main important points of our problem. So the way this works, this symbol, again, it's the same integral symbol that we used at the beginning of this unit for anti-differentiation, but now it has a lower and upper bound of integration. So that a and b value. So that is our interval on which we're trying to find the area. So a is always going to go on bottom, b will always go on top. So we always want a smaller value of x to a larger value of x. Then inside, we have our function. Again, that function's job is really to calculate the heights of the function. So it's still that same job. So instead of f of c sub I, it's just the regular function of f of x. So we don't have to come up with the formulas for our endpoints and then substitute them in to create those expressions. It's just the equation that is bounding the region that we're trying to find the area of. Again, another major benefit to using this. And then this dx quantity, well, that kind of takes the place of delta x in Newton's notation. So dx is just another way of representing that change in x, or the width of each of those rectangles. So again, the whole idea behind our Riemann sums and our sigma notations is we're taking the sum of the area of each rectangle by taking the height and width of each one. The heights come from y values, the widths come from x values, or f of x and some change in x. That is directly going to show up in these definite integrals. We still have f of x, which represents our heights, and that dx quantity represents our width. So that is the idea behind a definite integral. So we're going to practice translating these here in a second. But some bullet points, some nuts and bolts kind of stuff. So when we write the area of a region using that second notation, again, it goes by the name definite integral. That's what it represents, or that's the name of this thing when we see this guy. So for now, again, just because it looks similar to the notation that we used at the beginning of the unit, they are not the same thing, okay? So these two bullet points here to really explain the difference. An indefinite integral is what we did in the first section. So that is the idea of just going back from one function to the function that came before it. So an indefinite integral, something like the integral of cosine of x dx, that represents a family of functions. This is equal to sine of x plus c. So if this is my f prime, then this whole thing is my original f of x function. So an indefinite integral without a and b values attached, for right now, it has nothing to do with area. This is just going backwards to find those original functions. But as soon as I put a and b values on there, now this represents a different thing to us. That represents the summation of the area of an infinite number of infinitesimally thin rectangles. So it represents the actual area under that curve for the particular interval from A to B. So again, next section 4 or 5 is going to relate these two together. There is a connection between these, and we're going to learn it, just not right now. So for right now, think of them as totally separate things, okay? All right, so let's get some practice translating. So again, to be able to write Riemann sums, the limit of the Riemann sum, I need to know my function and my interval. Then everything else after that is us putting in some work. So that those two things are really easy to pick out from the definite integral notation. So right off the bat, I can see this first guy has an AB, or an interval from 2 to 6, and my function inside, again, the f of x part is everything inside this integral that's not dx, because again, it's my height times my width, or f of x times the change of x. So my function in this case is 3 natural log of x. So to write my limit for my Riemann sum, so I'm going to write the limit, and again, the new notation, we're going to start with the max of delta x sub I is approaching 0. So the limit of that for sigma from I equals 1 to n of my f of c sub I times delta x sub I. So again, we need something that looks like this guy. So this is where we would go through that process that we've done in the past. So first delta x of equal subintervals. So again, just because we're accounting for the idea that they're unequal doesn't mean that we can't still choose to do it the easy way, which is always using equal subintervals. This just accounts for if someone made us do it unequal, we can account for that and the process still works. But I'm still going to choose to do equal subintervals. So a minus b would be 4, so divided by n. My c sub I, again, my right endpoint would be my a plus delta x times I. So in this case, 2, because that's my a, plus 4i over n. Then for my heights, we would take f of c sub I. So I'm going to stick this guy into my f of x. So I would get 3 times the natural log of all this stuff. So for my Riemann sum, I'm going to take the limit of sigma of my heights times my widths. So I would have 3 natural log of 2 plus 4i over n times the width of each rectangle, which would be 4 over n. So obviously, I really hope that this is obvious. Once you wrap your head around the idea of these two different notations, these things are equivalent to one another. They are saying or telling you to do the same thing. They represent the same thing. Eventually, you'll learn how to evaluate them, and you'll get the same value. But working with this notation, and as we transition into the next section, allows us to hopefully never have to do the whole big giant limit process with all the I stuff ever again. This is just like when we learned derivatives. We learned the long way with limit definition first. Then we picked up on all the shortcuts because Newton and Leibniz did all the shortcuts or all the long stuff for us. So now we get to benefit from that and use the shortcuts. This is kind of that same idea, but as far as integrals go. So that's our first one. Second one, same idea. I got to pick out my interval. So in this case, I'm going from 0 to 3. And I want the area on that interval of the function sine of 5x. So that's my function inside. Again, it's everything but dx. So then my delta x would be 3 over n. That's the width of the interval divided by n subintervals or rectangles. C sub I would be my a plus delta x times I. So in this case, it's actually a really easy one, just 3i over n. 0 we don't need anymore. And then delta x is 3 over n times I. So then my f of c sub I, my heights, would just be sine of 5, because it's already in the argument with x, times my c sub I. So again, this formula will always be substituted into the function for x. So what I end up with is 15i over n. So now we have our height formula. So we're going to take our height times our width. So I'm going to get the limit as our max delta x sub I goes to 0 of sigma. Yikes, that was really bad. Apologies. Delta x sub I goes to 0 of the sigma from I equals 1 to n of sine of 15i over n times 3 over n. Again, that's such a mouthful, so long to write. I would much rather always choose to write these definite integrals, and hopefully I never have to take the limit of a sigma ever again. All right, so now we can do it in that direction, but now let's make sure that we can do it the other direction. So we're going to start with the notation we've been working with, and then we're going to try and translate it into the new stuff. This way is much more difficult, but it's still doable, so don't freak out or anything, okay? Again, to write my definite integral, I just need to know what the function is and what my interval is. So now we have to work backwards to find all that information. So in this case, the best place to start is with our delta x. So again, our delta x is always going to be multiplied by the function notation. So again, each one of these has a f of c sub I notation times delta x. So that's the easiest place to start. So our delta x is 3 over n, which means the distance between a and b, they are 3 units apart. That's what that top value in delta x is equal to. So we now have to go into the function to figure out what is the a value, so then I can add 3 to it to figure out the b. That's the tricky part of this, okay? So in the other part of this, so this whole big bracketed part, that is all of f of c sub I. So now what we have to do is go in and pull the c sub I out to get the function and also be able to identify our a value. So this is where it gets a little tricky. So you have to be on the lookout for something that kind of looks like our c sub I notation. So remember that c sub I, again, I'm never going to give you guys one where it's a left endpoint. That's just mean, because no one would ever choose to do it that way. But so for our stuff, our problems, we would be looking for an a value plus a delta x times I. And again, that delta x is always going to be some number the b minus a distance over n. So that part is what's really easy to pick out. So if there's something being added to that inside of something else, then that thing inside, that is my c sub I. For example, in this one, inside of this quantity cubed, that binomial, that is my c sub I. It has the exact same structure of a plus delta x. Again, it matches the 3 over n from the outside times I. So this guy is my c sub I, which means my a value must equal 1. That's where that 1 plus comes from inside of there. That also means then that my b value is 4. So I have the first part of my definite integral. Now the last part is coming up with the function. But again, if you can identify c sub I, then to figure out your function, we just pull the c sub I back out and x goes right back in. So if we do that, if we take the c sub I back out in this case and replace that with our x, we just end up with the function f of x equals x cubed instead of this big c sub I quantity cubed, and then plus 8. So to finish our definite integral, we take our function, and same notational rules apply as when we were working with these indefinite integrals at the beginning of the unit. If I have a function that's more than one term, then we have to put parentheses around it before we put that dx on there. Okay. So again, and just keep that in mind, this was originally a function of f of c sub I quantity multiplied by delta x quantity. So that's why we have to have those parentheses around there. Anytime we've got more than one term, this still whole thing represents the heights, dx still represents the width. So we have to multiply all of the height quantity by the width. So just to keep that in mind. But that is it. That is our new simple version of these previous problems. All right, let's try one more. This one's a little bit easier. Again, it's always a good idea to try and structure it as our heights times our width. So if we try to separate it that way, height times width, that width becomes our delta x. So delta x in this case would be pi over n. So again, that pi represents the width from our a to our b. Again, that doesn't tell us what either of those are. So until we actually go back in and find that a value with our c sub I. So now out of the heights, something in here is that c sub I quantity, and the only logical choice here is this argument for our sine function. So if c sub I was pi over n times I, again, we have to try and match that to an a plus delta x times I format. Well, there's the I, so strip that away. Here's delta x, so we can strip that away. Our a value, there's nothing being added here, so that means automatically my a value has to be 0. If a is 0 and delta x is pi over n, then that means b has to be 0 plus pi, or pi. So that is my interval. We're going from 0 to pi, and then if I take my c sub I out to write the function, we get f of x equals 2 times sine of x instead of that c sub I value. So this guy translates into the integral from 0 to pi of 2 sine of x dx. Now in this case, I don't need parentheses around the function. If you want to get into that habit, that's not a bad habit to have. You'll definitely always have them in there when it's absolutely necessary. But in this case, because it's only one term, it's multiple factors, but only one term, we don't absolutely need the parentheses. So a lot of times if you'll see problems already made up or written for you, you won't see them in there when they're not necessary. But that is all. That's our idea of translating into this new notation. So now that you've seen some examples with it and we can work with it a little bit, now we're actually going to start trying to evaluate them. So for example, our job for this one is to evaluate the definite integral from -2 to 1 of the function 2x dx. So what this notation means is I want you to find the area under the curve, or really it's between the x-axis and the function f of x equals 2x on the interval from -2 to 1. So here's the graph of this. The reason we're pointing this, or I'm giving you the graph, is because this is the first time for any of these area problems where we've seen part of the graph that's actually sitting below the x-axis. And we're going to reference that here in this process in a minute. So if we take this notation and translate it into our direction, well, right now, the only way to come up with the actual area, because it doesn't say to approximate, we want to know the actual value of this guy. So the value of this integral is equal to that area between the graph of y equals 2x and the x-axis. So when we do that, we need to, the only way that we can do that is using our Riemann sum, so our limits, okay? Well, there's another way, and I'm going to show you in a second, but for right now, when we see these kinds of directions, we can interpret it as the integral or using the integral, but then to actually evaluate them, that's when we have to actually switch back over to the Riemann sum. So this will be the max is delta x sub I goes to 0 of sigma from I equals 1 to n of, so my function is 2x, my interval is -2 to 1, so delta x would be 1 minus -2, or that's 3 units apart. C sub I would then be my a value, I don't know why I put parentheses there, my a value -2 plus 3I over n. So then f of c sub I would be 2 times that, so, or -4 plus 6I over n. So that's my formula for heights, that's my formula for width. So we will do heights times width. Okay, so now, again, this limit notation is how we start, but we accounted for that. We used equal subintervals. So now it's okay for us to simply state that if I know this is true, then the number of subintervals I have to have has to approach infinity. So now, inside of here, we are going to, actually, let's do two things. So let's move our delta x value out in front. So let me put that guy out here, okay? And then we are going to separate this into two separate Riemann sums. So I've got my limit as n goes to infinity. 3 over n is going to stay out in front. First guy, sigma of -4 plus, and then for the second one, I'm going to go ahead and pull out the extra stuff, 6 over n. Again, we want it to just be the i's, and then I inside. Now we can replace with our n formulas. So we've got the limit as n goes to infinity of 3 over n times, remember a constant is just that constant times n, plus 6 over n times our I to the first formula. Now we can distribute. Let's clean up the inside here just a little bit. So these n's would cancel, 6 over 2. This would leave me with a 3 up top. So if I distribute my 3 over n to all of that, my first term would become -12 because the n's would cancel. And then plus, then for the second guy, 3 times 3 is 9. And then it would distribute to both of these, so 9n plus 9. And then on bottom, n times, actually, I'm sorry, the 2's gone, so this would actually just be n on the bottom. So now when I take my limit, again, each piece makes a contribution, so limit of a constant is itself, plus the limit of 9n over 1n would just be 9. So we get a total of -3. So that is the value of this definite integral, and it's the answer to this question. But this is the issue that we come across. Up until this point in your mathematics education, you guys have always been told that area, because it represents two real-world dimensions composed together, has to be a positive number. However, in the realm of calculus, when we are talking about area between a curve and the x-axis, or area under a curve, there are some instances where a region is created using rectangles that go down from the x-axis or in a negative direction. So we have to interpret those slightly differently than we would in the past. So that's the next thing that we got to talk about. So when we refer to that, one way of describing that, because it is slightly different, is the idea of signed area. So again, all the different math that you guys have learned, we've always said that area can't be negative because it represents a real-life physical space. But that means this previous integral could not actually represent the area of the region created by the function and the x-axis. However, a definite integral's value can be positive, it can be negative, or it actually can be 0. But we've also would never say that the area of a region is equal to 0. So instead of interpreting these as just the area the same way we always have in the past, we're going to treat it as signed area. So eventually the area under these curves will take on real life meanings once we start to do some applications with these in a few, actually in our next section. So in those cases, those real world situations can take on negative values and have a real world meaning. So therefore, moving forward, anytime that we have a region that sits below the x-axis, it is going to have a negative signed area. Any region that sits above the x-axis will have a positive signed area. So it is possible to have both. So if we go back and we look at this problem, that's why this graph was given to you. So another way to evaluate this area, and you guys are going to get mad that you had to sit through this whole long Riemann sum, is if a function and the x-axis creates a known geometric shape, then we can use just simple basic geometry to evaluate the area. So it's only when we have these crazy different curves that they are not going to create known geometric shapes all the time. But in this case, my function is a linear function. So a slanted line and then the horizontal line of the x-axis, those two things paired together will always create a triangle, or in this case, two triangles. One with negative signed area because the region sits below the x-axis, and another with positive signed area because it sits above the x-axis. And in this case, if you really look at it, the negative signed area triangle is much bigger than the positive signed area triangle, which is why when I take that negative signed area and combine it with the positive signed area, because there was more negative than positive, we end up with a negative answer. So I could have done this with some basic geometry. My first triangle, again, this is going from -2 to 1, so -2 to 0. This has a dimension of 2. But because this side is going down, we kind of treat it as having a dimension of -4. So 1/2 of 2 times -4 gives me an assigned area of -4 for this region. This guy has dimensions 1 by 2 units, and it's +2 because it's going up from the x-axis. So 1/2 times 1 times 2 is a signed area of +1. Those two combined give me that -3 total. So it is a little bit different way of thinking about area in terms of what you guys have learned about in the past, but wrapping your head around that now and just treating it slightly differently will make an easier transition for us when we get to the real-world application problems. So moving forward, any regions that sit below the x-axis have negative values. Any regions that sit above have positive values automatically. So that's the big takeaway here. So our formal definition, if f is continuous and non-negative, so if we have a positive region, then it's easy. We can just think of it as typical normal area. But then when it's negative, we do have to warp our thinking a little bit. So if f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by this definite integral. So again, this is when we have a positive region, but when we have that negative region, we can still kind of think of it as area, but we know that it's sitting below the x-axis, so we're going to automatically come up with a negative value, okay? Now, some of these regions, again, are created by basic geometric functions, or functions that make basic geometric shapes. So to evaluate these, we don't always have to carry out the Riemann sums. If we have an easier method, we're always going to choose to do it the easiest way. So for example, I want to find the area between the x-axis and the function y equals 4 from 1 to 3. Well, if we sketch out that graph from 1 to 3, the function of y equals 4 is just a horizontal line. So a flat line and these two vertical lines at x equals 1 and 3, it just creates one rectangle with dimensions of 2 and 4, so it has an area of 8. So then this definite integral's value is the area of that region, or 8. Now again, I could have gone through the very long, painful process of setting up a Riemann sum and taking the limit of that, but it's not necessary because this creates a geometric shape, so we can use the shortcut. Okay, the next one, I want the area from x equals 0 to 3. Not sure why I drew that line out that far. Of the function y equals x plus 2. Well, that's a slope of 1 with a y-intercept of 2. So it looks like this guy. So when I sketch out this region, that area should look familiar. That is the area of a trapezoid. So if you recall, the area of a trapezoid is 1/2 times the sum of the two bases times the height, or in this case, width. So our first base on this side is 2 tall. On the other side, when x is 3, this linear function would have a y value of 5. So that's the second base. And then our height, or really our width of that trapezoid, that is our delta x, or the span of our interval. So that would be 3. So I would get 1/2 times 2 plus 5, or 7, times 3. So that has an area of 10.5, which means this definite integral has a value of 10.5. All right, now the last one, this one's a little bit trickier, okay, for two reasons. A, the function is trickier to work with, but now we're using variable of y as our input. So just for your own clarification, normally if I have y equals the square root of a constant minus x squared, that is the formula for a semicircle with radius of square root of c. So normally that would look like this guy. It's centered at the origin. Oh, yikes. That was really bad. Not even close. That's a little bit better. So a radius of c, square root of c units on either side. So the semicircle is centered at the origin. Its y-intercept would also be at square root of c. So that's the typical format for the function of a semicircle. It only produces positive y values because the square root on its own produces positive values. For the whole circle, I'd have to graph the negative version of that guy, which would plot the other half of the circle. But when I switch the variables out to the y's, then we flip-flop inputs and outputs. So x is now my output, but the square root still would only produce positive outputs, so positive x's. So in this case, it would be the right half of a circle. So in this case, it still works the same way. This constant inside, if I square root that, would produce the radius of the circle, which is why my interval goes from a y value of -2 to an x value of positive 2. So we haven't done any area problems where we use y as the input variable, but if we do, everything still works the same way. It's just instead of working across the region using rectangles from left to right, we move left to right because that's where small values of x exist and then big values of x exist. Well, with variable of y, it's still the same way. We would start with small values of y, so on the bottom side, and then we would work our way across the region towards larger values of y. So that's why our interval goes from -2 to +2. So that area, though, again, we don't need to do a Riemann sum. The area of a semicircle, or excuse me, a circle is pi r squared. So the area of a semicircle is pi r squared over 2. Well, I know my radius is 2 for this, so that would just give me pi times 4 divided by 2, or an area of 2 pi. So that is the value of that definite integral. All right, so now we're going to take a look at some basic properties. So if these definite integrals actually do represent the area or signed area of a region, then that comes along with some special properties. And a lot of these have to do with Riemann sums, which again, a Riemann sum, if we were to translate it back into the old notation, those Riemann sums are just the sum of a whole bunch of areas put together. So a lot of these properties are tied to properties of addition. So first off, this one's kind of like a trivial case, but it should make sense. If f is defined at x equals a, then the integral from a to a of f of x dx equals 0. Well, if this integral represents the area of a region from one value of x to another, if the top guy is the same value, that means there is no region. I couldn't draw any rectangles because I'm not moving. Or another way of thinking about it, again, these definite integrals should translate into f of c sub I times delta x. Well, delta x is equal to b minus a over n. But if both my endpoints for my interval are the same thing, a to a, then your width is 0. So no matter what the function is, all of the values being added together are just a bunch of zeros. So that's where this property comes from. Second one, if f is integrable, so to be integrable, that basically just means it's a continuous curve, a smooth, continuous region. I need to be able to calculate the area under that region. So if f is integrable on the interval a to b, then the integral from a to b of f of x dx is equal to the opposite of the integral from b to a. So earlier in the video, I mentioned that when we set these definite integrals up, we always want to go from the small value to the big value. Well, there's all kinds of crazy things that can pop up with these integrals, and sometimes, naturally, you will end up doing something that causes you to start at a big number and end up with a positive in just the setup process of the different things that we can do. The way we fix that is using this property, and it should make sense. If for some reason I wanted to set up an interval from 4 to -3, if I go about all of this the same way, my delta x is supposed to be equal to my b value minus my a. Well, -3 minus 4 would produce a width of -7 over n. That negative is the part that we don't really like. It's telling us that I have to go backwards 7 units. And we don't like to do that. So the way that we fix that is if I switch the order of these values, then I have to change the sign of the whole thing. Because if I go in this order and I multiply my heights by this negative delta x value, then it's going to produce a negative answer. But if I were to flip-flop my a and b values and make it go in the proper order, then it would give me a positive answer. So we simply change the sign of that integral. So that's the idea. So flip-flopping our bounds of integration, our a and b values, is what allows us to switch the sign of the entire integral's value. Okay? Third property, if a function f of x is continuous on the closed interval a to b, then f is integrable. So that was what we just talked about. That's just the definition of the term integrable. Then finally, the last one, this is kind of the transitive property of integration. So if f is integrable on a to b, so again, that just means there is a definite area for the whole region, then for any value c in the middle of the interval, the integral from a to b of f of x dx should be equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So visually, what that's saying is, here's my function f of x, here's x equals a, here's x equals b. So for any value of c that I want to pick in the middle of this guy, if I just pick a random spot, the whole area should be equal to this first area, a1, from a to c, plus the area of a2 from c to b, which kind of makes sense. If I take a whole thing and I break it up into 2 pieces, then as long as there weren't any issues in the middle of the interval, which is what it is meant by the fact that it's integrable, then I should be able to just take the 2 pieces, put them back together, and we get the total again. So this one definitely comes up a lot when we're doing different kinds of problems, but this one's shouldn't be too difficult to wrap your head around, okay? All right, so now we're going to put some of those properties to use. So for the first one, we want to take the integral from -1 to 1 of the absolute value of x dx. So again, right where we are right now in this process is very reliant on graphs. So we want to sketch the graph of absolute value of x. So you guys should remember this is that v graph. It's the graph of y equals -x on the left side, y equals +x on the right side. And we're going to go from -1 to 1. So that is my region, so -1 to 1. So it is essentially just 2 triangles. So because it's kind of naturally broken up into 2 sections, this is a really good place to break this guy up and use that last property. So I'm going to rewrite this as the integral from -1 of the absolute value of x dx, that's actually equal to the integral from -1 to 0 of absolute value of x dx plus the integral from 0 to 1 of absolute value of x dx. So that part is not like absolutely necessary. We don't have to actually write all that out, but that's essentially the math that we're going to do. I'm going to find the area of this guy using geometry because it's just a line, so we made a triangle, and then I'm going to find the area of the other section, put it together. So this is kind of a visual representation of that last property. Piece plus piece equals the whole thing. So sometimes we're forced to do this because of issues that occur in the middle of the interval. So in this case, the function is not discontinuous at 0, but it's not differentiable, and there's that sharp turn. So there are some issues with things like that sometimes. So this kind of acts like a natural stopping point. One section stops at that sharp turn, and a new one begins. So it's much easier for us just to evaluate each one. Another reason for that is when we learn how to actually do all of this stuff algebraically, each one of these guys is actually working with a different function. So the math is actually different for each one when we get to section 5 next, and actually have to do all this stuff by hand. Okay. Now, for the time being, these are both triangles with dimensions 1 and 1. So we have an area of 1/2 plus an area of 1/2. So we get a total area of 1. All right, next one. So this is another use of that same property. So given the area from -1 to +1 of some function f of x dx equals 3, and the area from 0 to 1 of f of x dx equals 5, we want to find the area from -1 to 0 of f of x dx. So if you look at the intervals, again, on a number line, there's 0. The first guy is going from -1 to 1. So this whole thing is supposed to have a total value of 3. But then from 0 to 1, so just this part, they gave us a value of +5. Well, by that fourth property that we just looked at, the whole thing is supposed to be equal to the two pieces added up. So if we were to set up an expression like we just did here, -1 to 1 of f of x dx is equal to the integral from 0 to 1 of f of x dx plus the integral from -1 to 0. Now, the order is slightly backwards. These two integrals could have been flip-flopped, but that part doesn't really matter. I have values for these first two. 3 has to be equal to 5 plus whatever the integral from -1 to 0 of f of x dx is equal to. So we can actually solve this like a normal equation. This value has to be whatever 3 minus 5 is equal to, which is -2. So the integral from -1 to 0 of f of x dx must be equal to -2. So what that really means is anytime that we see a total area is more than one of its parts, the other one has to be a negative. So just an example of what this graph could look like. Now, the first part, or I guess technically the second part, from 0 to 1 is +5, and we just found out that the first part, -1 to 0, is only -2. So that means part of the curve must be below the x-axis, the other part is above, but the part that is above has a much larger area. 5 is bigger than 2. So it could look something like this. So going from -1 to 1, I could have a small area of negative. So this region here could have an area of -2, but then I must have a much larger area for this positive region of +5. But the total area from -1 to 1 then would be the total of those two, and that's how we end up with 3. So those properties are going to pop up in a variety of different ways, so you just have to be alert to them and be ready to use them whenever we kind of have problems structured like this with pieces of information given to us. So for our last example, this one it's a summary question. It's basically going to put together all of the area stuff that we've learned up until this point, okay? So for the first off, the integral says we want to evaluate the integral from 0 to 8 of the function 2x minus 4 dx. So again, what that's really saying is I want to evaluate the area or know the area from 0 to 8 of the region under this function. okay? So the equation 2x minus 4, that's a linear function with a y-intercept at -4. So when x equals 0, we're actually going to start below the x-axis. It will cross the x-axis whenever this guy equals 0, which would be at x equals 4. When x equals 2, sorry. I was thinking 8 and did the math wrong. So when x equals 2, and then when x equals 8, we would have 16 minus 4, or 12. So I definitely made this too big, but we'll go just sketching it, okay? It doesn't have to be perfect. Okay, let's say that that is my region. So here will be x equals 8, there's 2. So we want to know the total signed area between the x-axis and this function. So really, I have two parts to that. So seeing the graph and knowing that now, I have that negative region, and then I also have this positive region. Now, when we go about doing this, if I do it graphically, when I sketch this graph and I try to find the actual area, visually I can see there's a negative part and a positive part. So I could do the geometry, which we're going to do here in a minute, to find this guy, and then make the first one negative, make the second one positive, and combine them. But when we go through it analytically or algebraically, and we actually do the limits and everything, we don't have to worry about changing anything. That will take care of itself naturally through the math because of the formulas that we choose to use. So it's really only visually when we see the regions below and above that we have to kind of think about it differently, okay? But like I said, we're going to go through basically everything that we've learned up to this point for these different problems. So the first part is I want to estimate that value of the integral with a left endpoint, then a right endpoint, and then actually with a trapezoidal approximation. So let's do that. So notationally, I can write the integral from 0 to 8 of 2x minus 4 dx is approximately equal to, and because we're estimating, we don't have the limit right now, so this would just be, and actually I don't need the sigma as well. So this would just be the shortcut way. So my delta x, because I'm picking a number of subintervals, this is the faster, easier way. So instead of an unknown value, I know my interval is 8 units wide, and I'm breaking that into 4 pieces. So my delta x would be 2, so that's the common width pulled out in front. And then my set of endpoints would start at my a value. So 0, 2, 4, 6, 8. And then I'm adding that delta x. But if I want to use a left endpoint Riemann sum, remember that would be the first 4. So f of 0, f of 2, and so on. So in this case, I have the graph, but the graph doesn't really tell me the whole story. So I actually need to substitute those values of x in here to get those y values. So my integral will be approximately equal to 2 times f of 0 would give me -4. F of 2 gives me 0. We already said that. Then f of 4 would give me 8 minus 4, so +4. And then f of 6 would give me 12 minus 4, or 8. These guys all total up to 0, so we end up with 2 times 8, or 16. So now visually, remember, we can decide, is that left endpoint a over or underestimate? Well, if I pick out any two values, because this graph is increasing, remember that a left endpoint will stick out or will stay below the graph. So this is an underestimate, okay? Now, if we flip things around and use the right endpoint estimate, now I have the exact same integral defined, but we are approximately equal to, it'll be the same delta x, still 2 units, but now I'm using these 3 values and 8. So right endpoints, f of 2, f of 4, f of 6, and then f of 8. So I already know these 3 values. Again, they're the last 3 here, 0, 4, 8. So the only one left to evaluate is my last guy, f of 8, which we already did earlier. That was 16 minus 4, or 12. So here I get 2 times 24, or 48. So if the left endpoint was my underestimate, then this must be my overestimate. So it means the real thing should be somewhere in between, okay? So we know the real thing somewhere in between 16 and 48. And in this case, when we get to our third part here, estimating the area using a trapezoidal approximation. Well, I don't know if we ever specifically stated this when we did these. Anytime that you use a linear function to bound your region, a trapezoidal approximation is no longer an approximation. That is the exact thing, okay? And that's because trapezoids, the way that we build them using this area model, we're always going to have a slanted edge up top, and that slant is going to perfectly lay on top of that linear function. So even though I'm going to set this up as an estimate, it's actually going to find the real answer for us, and you'll see that once we do part D as well. But we will write it out again as an estimation, okay? Because not every problem, if I switch this over to a quadratic, then it wouldn't be the exact value. So this is just kind of a refresher to summarize and make sure you guys all remember this process. Now remember, the trapezoidal rule is delta x over 2. That's the common width out in front. That is represented by this guy. But then remember, the area of a trapezoid, they also all have a 1/2 factor. So we pull that out as well. And then on the inside, this is the sum of all the heights. But remember that the interior heights, every height that is not on an edge, is used twice. It's used for the first trapezoid, but then it's also used for the one after that. So that is where we have f of x sub 0, or f of a, and then 2 times that next endpoint height, and then 2 times the next guy, and then at the very end, it's just f of x sub n. So all the interior ones get doubled, and then the ends only get used once. So in this case, my delta x, again, 4 equal subintervals, so delta x had been 2 this whole time, but I'm going to cut that in half. So now it's 1 out in front. And then on the inside, so now instead of just using the first 4 or the last 4, we're going to use all of them. So my first, let me scroll back up here. F of 0 was -4. And then 2 times the next height was 0. Then 2 times the next height, which was 4. And then 2 times the next one, which was 8. And then for the last one, then we take, let me scroll up a little bit. Then we will take our last height, which was 12, and add that on. So again, it's just the interior ones that get doubled. All the end values only got used once for one trapezoid. So then we go through and combine. So this guy is 0. This turns into 8, 16. Ooh. So we end up with -4 plus 8, which is 4, plus 16 is 20, plus 12 is 32. So that is our estimation of the area using the trapezoidal approximation, but also, again, because it's a linear function, this actually is the real area of this function. So, so that's trapezoidal rule, just a reminder. All right, now for the last one, for D, we're going to use or find the exact value using the limit definition. Okay, so one more time. So the limit as the maximum delta x sub I goes to 0 of the integral from I equals 1 to n of, now let's find our stuff. So delta x in this case is 8 minus 0 over n, so 8 over n. So then our c sub I is a, which is 0, plus delta x times I. So that would be 8i over n. Then our heights are this guy substituted into the function 2x minus 4. So I would have 2 times 8i over n minus 4. Or if I clean that up, we would have 16i over n minus 4. So that is the formula that we are going to substitute in here. Let me clean that up a little bit. So that is our formula for heights. This is our formula for widths. So that's what we're going to multiply together here. So 16i over n minus 4 times 8 over n. So again, all this process kind of just reworks itself the exact same way we've seen with others. So this is going to translate back into n going to infinity. And just to clear that up, the reason why we have to switch back to that notation is n is the variable that all of this is going to derive around, because we're creating a formula of n. So if I leave it in these terms, we won't have any variables that we can actually evaluate or take the limit of. But because this implies that n has to go to infinity, that's why we're allowed to make that notation switch. So I'm going to pull my 8 over n out in front, and then inside, let's go ahead and separate. So 16I over n will become 16 over n times the integral, or excuse me, the summation of I, and then minus the summation of our constant 4. So then we end up with the limit of 8 over n times 16 over n times the formula for sigma of I, which is that n times n plus 1 over 2. And then remember, for constants, it is just 4n. So let's clean that up, and then we'll take the limit. So n's cancel, 16 over 2 will reduce to 8. So when I distribute my 8 over n, I end up with 8 times 8 is 64, so if I distribute that inside, we end up with the limit of 64n plus 64. And then on bottom, we end up with the limit of, or excuse me, just n. And then minus, when I send it to the second part, that will be minus 32 because the n's will cancel each other out. So the limit of my first term, 64n over n, is 64, minus the limit of the constant is itself. And so we end up with 32. So again, just to reiterate, because the only reason that that estimate is the same thing as the real deal is because our function is a slanted line, which means the region itself really is a trapezoid, which is a little odd to think about, but again, if you do really think about it, I could actually make both of these entire things, those big chunks, even though they're triangles. A warped version or way of thinking is a right triangle is actually a right trapezoid where one base is 0 units long and the other is just non-zero in length. So the formula still works out. If I took 1/2 of base 1 plus base 2 times my width or my height, if one of the bases is 0, that's actually just the area formula for a triangle. So just be aware of that. It's just a little warped way of thinking about it. So again, another way that we can work with these area problems using that limit definition to find the real thing. But then our final thing that we've learned about these area problems is finding the exact value using integration. Well, that just means, well, I have my definite integral. And now it's up to me to find that area any way that I want to. So my options include, I can do the limit definition, so the limit process, which we just did. Or option 2, I can use geometry if the region created is a known geometric shape. Or option 3 is TBD. So option 3 is what we're going to learn in our next video. This is something referred to as the fundamental theorem of calculus. So for right now, we only have to pick between options 1 and 2, but after our next video, then you guys will have a third option, and this is definitely by far the most fun one. So that's what I would want to do. But in this case, we're limited. We've already done the limit process. We know that this is supposed to be 32, so let's just check it with geometry. So again, I have a region that looks something like this guy. This first one has a y-intercept of -4, x-intercept of 2, so this is -4 deep and then 2 across. So 1/2 -4 times 2, that would give me an area of -4. This guy is 6 units across in the x direction, 16 up, going up from there. Or excuse me, not 16, 12, sorry. 8 times 2 is 16, minus 4 is 12. So then half of 6 times 12 is 36. And 36 minus 4 gives me an area of 32. So that is our value of our definite integral. So this last problem is a pretty good summarization of everything that we've done up to this point with area. Okay, and again, like I've already previewed a little bit for you, our next topic is going to allow us to connect all the dots and learn how our anti-differentiation stuff ties into our definite integration.